Hi guys, we're going to go over 3.2a together, which is about least squares regression. Basically means line of best fit. So you guys are going to do this lesson, well, you're going to watch me teach you over this video, and then you guys will do the homework, and that will be kind of your task for the day. So in this lesson, we interpret the slope and the y-intercept of the least squares regression line. And again, least squares regression line is just a fancy name for the line of best fit. Use the least squares regression line to predict y for a given x. Calculate and interpret residuals and their standard deviation. And then last, we'll determine the equation of the least squares regression line using a variety of methods. And we'll do that a little bit more in 3.2b as well. All right, so let's just talk about the regression line. Linear relationships between two quantitative variables are definitely common and easy to understand. You guys have worked with them since you were probably in 7th or 8th grade. So a regression line just summarizes that relationship between your two variables, okay? Only in settings where the explanatory variable helps explain the response variable. So here is a little example. This is data for a Ford F-150, miles driven versus the price. You guys know that as you drive a car, the worth goes down, right? So the more miles we put on our Ford F-150, the less it is worth. So the red dots are obviously our data points. We had a Ford F-150 with 30,000 miles on it, and it was worth, $26,000, $27,000, so on and so forth. This blue line here, that's the line of best fit, right? It's what we call our regression line, okay? It predicts the price from the amount of miles driven. Okay. So it's a line that describes how a response variable y changes as the explanatory variable x changes. And we often can use the equation of the least squares regression line to predict a value of y for a given x. So for example, if I was looking to sell a Ford F-150 with 100,000 miles on it, I could use the equation of this least squares regression line to kind of figure out a good price that I could sell it for. Let's talk about interpreting a regression line. It's a model for our data, much like a density curve is a model for, normal data, for a histogram, things like that. The equation of our regression line just gives a compact mathematical description of what the model tells us about the relationship between x and y. So suppose that we have a y variable and we have an x variable. Here is how we write our regression line. Y hat, that's how you say that little guy on top of the y, we call it a hat. Y hat is equal to a plus bx. Okay, this is the same thing as you guys are used to, y equals mx plus b. We just use different variables in AP Stats. So the b is the slope, just like m was the slope before, right? It's the number in front of x. A is the y-intercept. So these are equations that you guys have worked with for many years. So in this equation, y hat is the predicted value of the response variable for a given value of x. That's why we put the y hat on there. That's what the hat is for. It's for the predicted, okay? It's not exact, it's a prediction, okay? Am I gonna sell my Ford F-150 for exactly as much as the regression line tells me I will? Probably not, it's a prediction. B is the slope. It's the amount by which y is predicted to change when x increases by 1 unit. And a is the y-intercept. It's the predicted value of y when x is equal to 0, right? That's where the y-axis is. It's when x is equal to 0. All right, so we got our Ford F-150 data again. Here is the equation of that blue regression line. The predicted price is equal to 38,257 minus 0.1629 times the miles driven. So see how I directly inputted my variables in for x and y. Okay, predicted price, miles driven. You can either define them separately or you guys can define them in the equation like that. So let's identify the slope and the y-intercept, and then we'll interpret each value in context of the problem. Okay, so the slope, we'll do that one first. The slope is the number in front of x, so in this case it'd be negative 0.1629. So this tells us that the price of a used Ford F-150 is predicted to go down by $0.1629 or 16.29 cents for every mile we drive that truck. So if we drive our truck 1 mile, the price is going to go down $0.1629. Okay, the negative means the price is going down. The y-intercept, 38,257, that's the predicted price of a Ford F-150 with 0 miles driven. Okay, when X is 0, aka 0 miles, that's how much our Ford F-150 is going to be worth. We can use our regression line to predict the predicted y for any value of X. So back to our little Ford F-150 data. We can use the equation of our regression line to predict the price of a Ford F-150 with 100,000 miles driven. Okay, so we can see what it represents graphically. At 100,000 miles, the price, it looks like it's going to be about 22-ish thousand. We can get an exact number or an exact prediction using our equation. Input 100,000 for our X variable, miles driven, and then just compute the predicted price. So if we do that in our calculator, we get the predicted price is $21,000, or $21,967. Okay, let's talk about extrapolation and interpolation. So we just used our regression line to make a prediction for what our Ford F-150 would be worth using, or for 100,000 miles. We can substitute any value we wanted in for X, right? If we go back, let's look at that slide really fast. We could plug in anything we wanted for X. We could plug in 1,000,000 miles. That probably wouldn't make sense though, because I don't think you could drive a Ford F-150 for 1,000,000 miles. We could have even plugged in -20, but again, that wouldn't make sense either because you can't have a truck with -20 miles on it. Okay, obviously 100,000 makes sense. That's a reasonable value for how much you drive a car. So, while we can substitute any value we want in for X, only some of them make sense. So extrapolation is using the regression line for predictions far outside the interval values of our explanatory variable. Such predictions are often not accurate. So if I had used my equation to plug in 1,000,000 miles, that's extrapolation, okay? It's outside the range of our data. Our data ranges from about 0 miles to about, looks like 150,000 miles. Anything outside of that range is going to be extrapolation. Interpolation is the use of the regression line for a prediction inside the interval of values of the explanatory variable X. So we just made a prediction for 100,000. That was inside the range of our data, right? Our data went from about 0 to 150,000. So what we did in the last example was we used interpolation to predict what our Ford F-150 would be worth with 100,000 miles driven on it. Don't make predictions using values of X that are much larger or much smaller than those that appear in your data, okay? It's extrapolation. It's often not accurate. If I plugged in 1,000,000, it wouldn't have made any sense. All right, let's talk about residuals. In most cases, no line will pass exactly through all the points on your scatter plot. It's a line of best fit. It's not a perfect line. A good regression line will make those vertical distances, though, as small as possible. So a residual is the difference between an observed value and a predicted value. We have a little equation for that. The observed y minus the predicted y minus y hat. So all of these little black lines here are residuals. It's the difference between the observed value. The observed value is from our data, right, the red dot, and the predicted value, which we get from our regression line. If we want our line of best fit to be accurate, we want these vertical deviations to be as small as possible. Of course, it's not ever going to be perfect, right? Ideally, all of our points would fall exactly on this line, but again, it's a prediction. So it's not, it's the line of best fit. So again, residuals, we want to be as small as possible. And here, all of these black lines are the values of the residuals. All right, so we're going to do an example together. Don't you hate it when you open a can of soda and some of the contents spray out of the can? Mr. Freund was over at my house one time and he opened this 2-liter can of or 2-liter bottle of Sprite, and it went all over my floor. And if you've ever spilled soda on your floor before, you know that it is sticky and it will never come off. So that made me angry for a little while. Anyway, 2 AP Stat students wanted to investigate if tapping on a can of soda would reduce the amount of soda expelled after the can has been shaken. I don't know if you guys have heard of that. I don't know if it's a myth or not, but you tap the top of the can to see if it will reduce the amount of soda that sprays. So for their experiment, they vigorously shook 40 cans of soda and randomly assigned each can to be tapped for 0 seconds, 4 seconds, 8 seconds, or 12 seconds. And then after opening the can, cleaning up the mess, the students measured the amount of soda left in each can. So here's our data, here's our scatter plot. You can see our data for 0 seconds, so this is how much was left in the can, right? You can see at 0 seconds, there was definitely less soda left than when we tapped for 12. Here is our regression line. The predicted amount of soda left is equal to 248.6 plus 2.63 times the amount of time we tap. So let's interpret the slope and the y-intercept. So this guy is our slope, 2.63. So let's go ahead and interpret that. Slope of 2.63. So for every additional second that we tap, the amount of soda left in the can will increase by a predicted 2.63 milliliters. That word predicted is important. It's not going to increase by exactly, class is over. It's not going to increase by exactly 2.63 milliliters. It's going to increase by a predicted 2.63. Okay, so that's an about. It's not exact. So make sure you throw that word predicted in there. Okay, y-intercept, that's this guy, 248.6. So y-intercept of 248.6. So if we tap the can for 0 seconds, the predicted amount of soda left in the can is 248.6 milliliters. So let's predict how much soda would remain in the can if we tapped for 10 seconds. So here we are going to plug in 10 for tapping time. And then we can go ahead, plug that into your calculator and figure out the predicted amount of soda left. All right, so simplifying, we get the predicted amount of soda is 274.9 milliliters. So if we tap the can for 10 seconds, we'll have a predicted amount of 274.9 milliliters left in our can. Number 3, should we use this regression line to predict how much soda is left after tapping for 60 seconds? No, 60 seconds, that's way out here, right? 60 seconds. That would be extrapolation. Our results probably won't be accurate. 60 is so far outside the range of our data, right? Our data ranges from 0 to 12 seconds. So we don't know if this trend continues. We don't know what happens after 12 seconds. So using our equation to predict for 60 seconds, it's not good practice to use it because, again, don't know if the trend continues. So that's extrapolation. Our results probably won't be accurate. All right, number 4, let's find and interpret the residual for the can that was tapped for 4 seconds and had 260 milliliters of soda remaining. So that's this guy, 4 seconds, and we got one with, well, we had a couple with 260. But. All right, so a residual is equal to y minus y hat.